So today we're going to manually review on the numerical representations and the building blocks sections. And if we have more time, we are going to review the sequential circuits and give you some basic idea about latch and the flip-flop. So, okay. Well, okay, so why there's so actually I think we already mentioned about the binary representations, and here are three possibilities we can use to represent their signed numbers. And the first is their signed magnitude. So namely, we just take their absolute values of these numbers and transform into their binary format. And then according to the sign of it, we are going to assign 0, 1 to these binary numbers, to the most significant bit of these binary numbers. And if we have the positive numbers, then their MSB, the most significant bit should be 0. And if we have negative numbers, and actually the most significant bit should be 1. And that's one possibility. And actually, for the sign magnitude representations, so we have two possibilities to represent the number 0, right? Because 0, 0, 0, 0, with 6, 0, we can represent the number 0, and with the MSB as 1 and the left bit as 0, we can also represent the negative 0. And for the ones complement representations, so similarly, we just do we just transform the decimal numbers to their unsigned binary numbers, and then according to the sign of these numbers, if the number is positive, then we get our result, and if the number is negative, we are going to flip all the bits. Right? And for twos complement, we just do a further steps after doing the ones complement. So actually, after get the representations of ones complement, then if this number is negative, we are going to add a +1 with the ones complement representation to get the representation of twos complement, right? And so actually, but how could we just transform the twos complement number back to decimal numbers? Should we just use different equations to transform their negative numbers, namely the MSB is 0 or 1? Maybe we have different equations to transform the twos complement number back to decimal. Is it? Or we can find a uniform equations to transform twos complement numbers, whether MSB is 0, 1 to decimal. And the truth is that we can do that. And the equation should look like this. So for the positive numbers, so the MSB is equal to 0. Actually, we just the decimal of representation of these twos complement number can be gotten from these equations, right? And if the twos complement number is negative, namely the MSB is 1, we can get this equation. So the decimal representation of this twos complement number should be minus 2 to the n minus 1 minus this summation. And actually, so if we try to combine these two equations together, we can get these equations. Okay, sorry, I will just wait a few minutes. So actually, so the only difference here is that I is equal to 0, n minus 1, bi to I, right? Actually, these two parts are the same, right? The only difference is that for the negative numbers, we just minus 2 to the minus n minus 1, right? But for the positive numbers, we do not do this subtraction. So actually, we can just combine these two equation together to get a uniform equation, and it should be look like this, and it should be bi minus 1 times negative 2 to the n minus 1 times the summation to 0 until n minus 2, and bi times 2 to the I, right? And actually, that's the uniform representations for choose complement number. And according to these, you can find the maximum number we can represent by using the choose complement number, right? So if we want to get the maximum numbers using choose complement, what we should do? If we want these equations to be maximized, what we should do? So notice that all these coefficients should be positive, right? And this coefficient is negative. So if we want to get maximum numbers, what we should do for each bi? So we just want this bi minus 1 is equal to 0, so that we do not do subtraction, right? And for each bi where I is less than or equal to n minus 2, we will let it be 1 so that we can get maximum number, right? Is it clear? So actually, according to this, the maximum number we can get should be the maximum number. So I will just should be 2 to the n minus 1 minus 1. Is it clear? And if we want to get the lowest number, or if we want to get the smallest number, namely is a negative number, what we should do for this? So we just want, since all these coefficients are positive, so we just want to order bi with positive coefficients as 0, and the bi with negative coefficients as 1, so that we get minimal number, right? Is it clear? So actually, the minimal number we can represent should be sorry. Is it clear? So actually, you may find the maximum number we can represent and minimum number we can represent is not symmetric, right? Is it clear? Because the minimum number the absolute value of the minimum number is not equal to the absolute value of the maximum number, right? That's because we only have an unique representation for 0, right? So that because we have to let the maximum number minus maximum number is equal to 2 to the n minus 1. And then we just add 1 since we have a 0, so that it means that we have 2 to the n different notations for different numbers. Is it clear? So actually their unsymmetric is caused by their unique representation of the number 0. And actually for the sign magnitude and 1's complement representations, the interval it can represent it is symmetric because we have 2 different representations to represent the decimal 0. Is it clear? Okay, you can see here. Here is that how we represent the decimal numbers from 0 to 7, or from positive 7 to negative 7. So you can see here, for sign magnitude, we have 2 different representations for 0. For positive 0, we have 0, 0, 0. For negative 0, we have 1, 0, 0, 0. And the same for the sign, for the 1's complement. And for the 2's complement, we only have 1 representation. Okay, and actually, this questions is just trying to help you for the quiz 1, actually. It's really simple, right? Because we can just do the similar things as decimal addition. What we do, we just 1 1 0 1 0 1 1, and right, and it's quite similar as decimal addition. And then what we do, we just do addition from the least significant bit, and if we find the addition result is just overflow, we will just have a carry out signal, namely the carry in signal for the next bit, right? And then we will just do it for you. So first, 0 plus 1 is equal to 0, right? And there's no carry out signals. And then we just do 1 plus 1, which is equal to 2, namely 1, 0, which means that we have a carry out signal. So we will just use this denotation to represent we have a carry out signal for the bit 2, right? And then 0 plus 1 is equal to 1, and there is no carry out signals, and 1 plus 1 is equal to 1, 0, and we have a carry out signals. So we just use this denotation to represent we have a carry out signals for bit 4. And then we just do addition for 1 plus 0 plus 1, and is equal to 0, which is overflow. So actually we have a carry out signals, and the summation result should be 0, and we just use this. Okay, is it clear? So you can do the verifications by transform these 2 binary numbers back to decimal, and then just do addition in the decimal domain, and then just transform the decimal result back to the binary numbers and to do the validation, right? Is it clear? So actually, what we have here, we have 3, and it's equal to 15.6, right? And this is equal to 15.6, and this is equal to 9, and this is equal to 6 times 16, 19, and this is equal to 105. And you just do addition, and actually they're the same. They should be the same. And here is just for question 1.2, and you just you're asked to do the unsigned binary subtractions. So actually, according to the problem sets, all these numbers should be treated as unsigned binary representations instead of signed magnitude or the 2's complement or 1's complement, right? So you have to get the representations from the problem set. So which representation we're going to use for these numbers. decode these numbers, right? And according to this problem set, these two numbers are just unsigned representations. So namely, these should be 9, and this should be 4, and the result should be 5, right? And we just transform the 5 to the unsigned binary number, and it should be 0, 1, 0, 1, right? Or you can just use subtraction similar as the decimal subtractions, right? So what we can do here is that we will just do subtractions similar as the decimal subtractions. So just list these two operands in horizontal line, and then we just do subtractions from their MSB, the most significant bit, right? I'm sorry, it's here from listing, right? So 1 minus 0 should be 1, right? And 0 minus 0 should be 0, right? And 0 minus 1 should be 1. And we have how could we say? So it means that we just need to borrow 1 from the next bit, right? And actually, it means that we will have a signal here for the MSB. It's actually right. So for the MSB, the result should be 1 minus 0 minus 1, and the result should be 0. Okay, is it clear? So we are just trying to read in the binary numbers, and so we're going to convert the number below to decimal, and you can see from the problem set. So we say these notations is their sign magnitude notations. So you are going to transform these numbers back to decimal notations according to the principle we talk about for the sign magnitude. And what do we do here? So actually, for the sign magnitude, the MSB here does not influence the absolute values of these numbers, right? Is it clear? So the MSB just affects the sign of these numbers. And if the MSB is 0, it means that the number should be a positive number. And if MSB is 1, it should be a negative number. That's the principle for sign magnitude, right? So if we're going to transform their sign magnitude back to the decimal, we only need to care about for the absolute value of these numbers, we just need to carry about the following, the bits without MSB, right? And how could we transform these unsigned numbers to decimal? It's quite simple, right? We just use the equations we are familiar with. It means that we have 2 to the 4 in their decimal notations, and 2 to the 2 in the decimal notations, and 2 to the 1 in these decimal notations, and 2 to the 0 in decimal notations. And the result should be, and the absolute result should be 2 to 4 plus 2 to 2 plus 2 to 1 and plus 2 to 0, and the result should be 23. And that's the absolute value for this number, right? And since we have MSB as 1, so actually the final result should be negative 23. Is it clear? And that's quite similar. You may find actually the only difference between these two numbers is that we have MSB as 1 for this number, and we have MSB 0 for this number. So actually the absolute value for these two are the same. The only difference is that we have and one is positive and the other is negative. And actually this should be the positive number, right? And the result should be 23. Okay, it's dear. So we're going to transform this ones complement representation back to decimal. And we are going to follow the principle we talk about for the ones complement. So we will still look at the MSB, and since the MSB is 1 here, so it means that we have so actually this number is a negative number, right? So if we want to get the absolute value of this negative number, what we do? We're going to flip odd bits, right? So what we do, so we'll flip. So since MSB is 1, so we are going to flip odd bits. And after flipping odd bits, the result should be 0, 1, 0, 1, 1, 1, right? And actually, that's their absolute value for this negative number. And actually, the absolute value of this number, how could we get the absolute value of this negative number? Is similar, right? We just transform this binary. We just treat this number as unsigned binary number and transform it to the decimal number. And then the decimal number for this unsigned representation should still be 23, right? It's still 23 actually. And since we have 1 here, so actually we should just add a negative symbol here. And the result should be negative 23. And here is another problem. We are going to convert the choose complement notation back to the decimal notation. And actually, we can do the same steps for the choose complement. So what's the meaning of it? So if you want to transform so we have two ways to do the transformation. And the first step is that since we find we have a 1 here, right? So actually it means that this notation just represent a negative number, right? And according to the principle we talk about for choose complement, we just do the transformation in reverse order, right? So actually, so what we do for choose complement, so first we just flip odd bits and then we just add 1, right? That's how we transform our negative or transform our positive choose complement number to its negative representation, to its negative version, right? So actually we just do the reverse way. First, we just -1 to this number. And then after get the minus, got the subtraction result, we just flip odd bits to get the absolute value of this binary notation. And then we just transform this binary notation to the decimal notations and just add a negative symbol to finish our transformation, right? And actually, first, -1, and then flip odd bits, right? Because if we is it clear? Is it clear? So we just first -1 and then flip odd bits. And actually, we also have another possibility to do the transformation. And we just, is still the same. You just flip out bits. And then add 1. And actually, this result should be the same. You can, I will do it for you. You can just, so for the first method, what we do after we minus 1, what we should get should be 1 0 1 0 0 0 0 or 3 0, sorry. 3 0, right? And then we flip out bits. Result should be 1 1 0 1 1 1, right? That's the result we get by using the first 2 steps. And then we can also use the second method to do the transformation to get the absolute value of this representation. So, and the result should be, so first it's quite similar. We flip out bits and it should be 0 1 0 1 1 0, and then we just add 1. And they are the same. And exactly the same result, right? And so you can say so whatever the number it is, so whether it's MSB 0 or 1, if we just want to get its negative representations, we can just follow these principles. So we just, for the positive numbers, we just flip out this and add 1. And if we want to get the absolute values of the negative numbers, so which means that the MSB is 1. So we can also use these 2 steps. Is it clear? So if we want to transform a positive number to the negative numbers, we can use these 2 steps. And if we want to transform a negative number to the positive numbers, we can still use these 2 steps actually. Is it clear? So the transformation, we just share the same steps for the transformation. Okay, so according to the results we find for question 2, so what we do if we want to transform the following 2's complement to decimal, so the first step is that, right? So accordingly, so we just want to get the absolute values of these three 2's complement representations, right? Since how could we get absolute value of these 3 negative numbers? So we just follow the steps we mentioned about. So first we flip out bits. 0 0 1 1 0 0, and then we just add 1. 0 0 1 1 0 1, and then the absolute value of this number should be 11, right? So actually the decimal representation is minus 11. And similarly for 2 and 3. Or we can just use, and that's the first step we can do, right? That's the first method we can do, or we can just use the unified representations for 2's complement numbers, right? How could we get this? So actually it means that if we want to transform this 2's complement to decimal, so it means, so according to the binary representation here, it means that we are going to have 2 negative 2 to the 5 in our decimal representation, right? So the number is equal to, and we have a positive 2 to 4 in our decimal representation. And we have a positive 2 to 1 in our representation and a positive 2 to 0. And this result should be negative 32, and this should be positive 16. This should be positive 2. This should be positive 1, right? And the result should be what? Oh, sorry, this is not -11. This should be -13. Sorry about that. Because we have 8 here, and we have 4 here, we have 1 here. The result should be -13. Sorry about that. And by using the uniform equations for the choose complement number, we can still get the -13, right? And we can do the similar things for the second representation and third representations. You can try it by yourselves. And that's the question 3.2. You're going to write the decimal numbers in sign magnitude 1s and 2's complement form. So actually, you're going to use 8-bit sign magnitude 1's complement and 2's complement. So actually, for the sign magnitude, you have to transform the decimal to the 7-bit unsigned number, right? Because we have to use the MSB as the signed notation. So actually, first step, if you want to transform the decimal to the 8-bit sign magnitude, you have to first transform the decimal 10 to the 7-bit unsigned number, right? How could we do the transformation? So the result should be, so it's quite similar. So we just transform the 10 to right? And first, we just transform the decimal 10 to the 6-bit, the 7-bit unsigned number, and then according to its sign, we are going to assign 0, 1 to its MSB, and since it is positive, we will just assign 0 to its MSB. So that's the 8-bit sign magnitude for the decimal 10, right? And actually, for the choose complement and for the 1's complement and choose complement, since the decimal 10 is positive, so actually, the 1's complement representations for decimal 10 and choose complement representation for decimal 10 should be all the same for sign magnitude, right? So actually, they're the same. 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. And for choose comp, and for the, if we want to transform the -11 to the sign magnitude, it's quite similar, right? So first we just ignore the symbol, the sign symbol for this number, and we just transform the absolute values to the 7-bit unsigned number. And then we're going to assign the MSB according to its sign. And so how could we transform the 11 to the 7-bit unsigned number? We just use the subtraction method or the division method, right? So we are going to first divide 11 by 2, and we just get the modular of this division and get the result of this division, and then we are going to use the result of this division and divide it by 2, and until we get decimal until the division result is 0, right? So actually, that's the 7-bit representation for 7-bit unsigned representation for their decimal 11, right? And then since we have a negative symbol here, we're going to assign their MSB as 1. Right? And how about the 2's complement version for negative 11? So we will first, so what we do, how to get the 1's complement for the negative 11. So first we were going to write the unsigned, we are going to write the 8-bit unsigned magnitude, right? We are going to write the 8-bit unsigned binary representation for the absolute values. And then since we have a negative symbol here, we just flip all the bits of this representation together 1's complement representation. Is it clear? If so, actually, for 2's complement, for 1's complement and 2's complement, we just ignore the sign symbol and we transform their absolute value of its decimal of their decimal numbers to their according to the requirement. And here the requirement is that the 8-bit representation. So we just transform the 11 to the 8-bit unsigned binary representation. And then since we have a sign symbol, since we have a negative symbol here, we just flip all the bits of the unsigned 8-bit representations to get their 1's complement representation. And the result should be 1, 1, 1, 1, 0, 1, 0, 0. And for 2's complement, we just add 1 for this representation, right? And the result should be 1, 1, 1, 1, 0, 1, 0, 1. And you can do for the following notations, and that's quite similar. And here is the question 4. You are asked to do subtractions for the 2's complement binary numbers. And how could we do this? So we just need to notice that the subtractions is the subtractions of, well, let's say if we have A minus B. So if we are going to subtract A by B, so actually it is equal to that A plus minus B, right? They're the same. The result should be the same. So actually for the 2's complement, so for the subtractions for the 2's complement, we can also apply these rules. And what we do is that for the first notation, since we are going to negate these numbers, we can just apply the 2 steps we mentioned before, right? So what do we do if we are if we want to negate these 2's complement number? So first step is that we flip all bits, and then we just add 1, right? And the negation of this number should be so first if we flip all bits, the result should be 0, 0, 1, 1, 0. And we add 1, the result should be 0, 0, 1, 1, 1. And then we just do addition. So actually the result should be 0, 1, 0, 1, 1. Oh, sorry. Right? It should be 0, 1, 0, 0, 1, 1. In 2's complement. And for question 2, it is quite similar. And we are going to flip the 0. We are going to negate this 0, 0, 1, 0, 0. And the negation result should be 1, 1, 1, 0, 0. Right? So first we'll flip odd bits. And the result of flippation should be, oh, I don't know the number. Actually, the result of it should be 1, 1, 0, 1, 1. And then we just plus 1. And the result should be 1, 1, 1, 0, 0. And we just do addition for these two numbers. And what we get? So let's do it. 1, 0, 1, 0, 0, 1. Right? And actually, we have an overflow bit here. And what we do for this overflow bit? So we have to. So we have to take care of this overflow bit. So what's your problem? Oh, so thank you. Well, let me just check it once again. Yes, you're right. Thank you. And okay, so actually we have an overflow here, right? So what we should do? So should we discuss it or just remind it? So let me just check. So first, what we are going to do is just, so here is my method. I don't know the standard way to do to get a result. So actually, to validate what we are going to do for this overflow bit, so we are going to transform these numbers back to their decimal notations, and then we're just trying to do addition, do subtractions, and what's the decimal representation for these two complements, and it should be negative 15, right? No, negative 7, right? So we just flip out bits 0, 0, 1, 1, 0, and just plus 1. And that's the absolute value of this two complement notation. And since we have MSB as 1, so actually we have to add a negative symbol. So actually this just represents negative 7, and this represents the 4. And we just do subtraction, the result should be negative 11, right? And if we want to transform the negative 11 to the, so actually you can see here, the result does not overflow, right? The result of the decimal notation does not overflow because the maximum the minimum number we can represent for the 5-bit choose complement should be negative 16, right? Is it clear? So actually, since this subtraction result does not overflow, it means that this result is not overflow as well. So we just discussed this overflow bit because according to the decimal result here, we don't need this overflow bit. And right? If we just discuss this overflow bit. But actually, so actually, well, the truth is that, okay, sorry. But actually the truth is that we don't care. If we discuss this result, this overflow bit here, we still get the correct result. If we just remind this overflow bit, we will still get the correct result, actually. Because these two are the same. So actually we can just expand numerous one here. And we can still get correct result. Right? Because what we do, we just flip out bits. And since we are just flip 1 to 0, and 0 just represents it, just means that we don't have this component in our decimal notations. So actually this 1 here does not affect our result, right? So we can just add numerous 1. Or infinite 1 here, right? So actually, but we can just represent. And the only case we should take care of this overflow bit is that this bit is 0. We should take care of this overflow bit, actually. Why? So, for example, let's say so if we are going to do an addition for the 1111 in 2's complement plus 0001 in 2's complement, the result should be what in 2's complement? It should be, so it should be 1000, right? And here we will also have an overflow bit. 1 here, right? Right? Is it clear? And actually, this overflow bit should be discussed, actually. I think because we will just use the decimal notation to validate our result, because for 1111 in 2's complement, it just represents the negative 1. And for 0001, it represents positive 1. The addition result should be 0. So actually here we have to discuss this overflow bits. But in this case, we don't need to. We can just remind this bit and it will not affect our final results. And for this case, think about 1001 minus 0100. And actually, in this case, the result should be what? So it's quite similar, right? So first we will just negate this number, right? The negation of this number should be 1011 plus 1, right? 1011 plus 1 should be 1100, right? And in this case, what do we get? That should be the result, right? Is it clear? That should be the addition result. And how about this? should we just discuss this overflow bit or not? So we have to consider it carefully. And because if we discuss this overflow bit, we may get a positive number, right? If we just remind this overflow bit, we will get a negative number, right? But for this case, if we discuss this overflow bit, we will still get a negative number, right? For this case, for the sub-question 2, if we discuss this overflow bit, this is still, the result we get is still a negative number, right? And if we just remind this overflow bit, the result we get is still a negative number. But in this case, if we just discuss this overflow bit, we will get a positive number, right? And we remind this overflow bit, we will get a negative number. So actually, here is my method. So we just validate whether we should remind this overflow bit or not according to the decimal result, according to the corresponding decimal result. All right, because what do we do here? Is that, so the 1001 in decimal notation should be represented -7, right? Should be -7, right? Is the -7. And this should be still 4, right? The subtraction result should be still -11. But in this case, the smallest number we can represent in 4-bit 2's complement representation is -8, right? So the subtraction result -11 just exceed the minimal number we can represent. So it means that the overflow bit just makes sense. Is it clear? Otherwise, because the minimum number we can represent in 4-bit 2's complement is -8, but the result we get here is -11. So it means that if we just use 4-bit 2's complement number, we cannot represent this -11. So we have to use 5-bit 2's complement. Is it clear? So this overflow bit just makes sense. And actually, the question 4, we already discussed it in the last discussion section. It's quite similar, right? So there are 2a plus 3c. What we do? So a plus c should be 22. Namely, you should have an overflow, or namely carry out signal, right? Next one, and the summation of the a plus c should be 6, right? And we have an overflow signal, and the final result should be 16.6 in hex or in base 16. Okay, okay, so actually, how could we represent fractions using binary notations? So did the professor talk about it or not? Yes, okay, that's great. So actually, we can still use the principles of the decimal of the binary notations, but actually here, the 0 after this point is just okay. So do you remember for integers what we have for the binary notation? It should be that's the notation for integer, right? So namely the part before this point, right? But for the part after this point, the notation should be what? Should be look like this. So that we can represent the fraction. So according to these notations, what do we have? So according to this one, we have 1/4 in our decimal notation, right? One fourth, and we have 1/8 in our decimal notations, and we have 1/32, 30 seconds in our notation, right? In our 1/32 in our decimal notation. So we just do addition. So here is 1/4, here is 1/8, and here is, so the addition result should be, here is 8, 4, 1, and that's the result, right? Right? Okay, so that's how we transform the binary numbers, their binary fractions, to decimal fractions. But how could we transform our decimal fractions to binary fractions? So it's quite similar as what we do for integers. But in this case, for the parts, after these points, we would just do multiplications instead of divisions. Right? So for integer parts, we will just do we will do divisions to get each bit, right? But for this part, we will use multiplications to get each bit. So what we do, first, we are going to multiply these fractions with 2. And then according to the multiplication result, the multiplication result is 2, 0, 5, 7, 3, 1, right? Is it right? Right? That's the multiplication result. And then since we have integer 1 in the, since we have a 1 in integer parts, so actually this means that for this decimal notations, for the binary, so it means that we are going to have, since we have, so it means that we are going to have 1 second in our binary notation, right? Is it clear? Because the multiplication result has an integer 1 here. So actually, so it means that for these decimal fractions, we are going to have 1 second in, right? Okay, since we have 1 second, so actually it means that we are going to have 1 here, right? Is it clear? Yep. Okay, so actually we just discuss the integer parts and just do multiplication for the fraction parts once again. Okay, so we would just discuss this, and the result should be 1, 5, 7, right? Should be 7, right? 0, 0.10. And since we don't have an integer part for this multiplication result, it means that we don't have 1/4 in our binary notation. So we will just use 0 here. And then just use multiplication once again. And the result should be 1. Right? And actually, since we have an integer 1 here, it means that we have a 1/8 in our binary notation. So we just use 1 here. And then we just discuss the integer parts and do multiplication once again. So we have 0, 0, 0, 1, 7, 6, right? Oh, okay, yes, that's correct. So according to the multiplication result, it means that we have 1 here. So actually, since we still have, so the friction part is still not zero. So we have to do multiplications until the friction part is zero, right? Until the friction part is zero, then we finish the transformation. But actually, we can never get the friction result as zero here. So it means that for these binary, for these decimal fractions, we will get circulating binary notations if we want to precisely represent this number in binary. And that's quite similar for decimal notations, right? Because if we want to represent 1/3 in decimal notations, we still need to use circulating decimal, right? Is it clear? Because, and so it means that not every numbers in decimal could be represented using finite bits of the binary if we want to represent it precisely. So the precisely means that the result has no errors. But actually, but the truth is that, so in the real world case, we just allow some errors. So maybe we just say that maybe until we get some tolerable arrows, then we just end our transformations. But if we want to represent these numbers precisely, we have to use circulating binary or infinite binary. And just this case, just want to mention this phenomenon. But actually, in quizzes, I don't think the professor will ask you to transform decimal fractions to a circulating binary. You don't need to worry about this. So actually, I just want to give you these ideas. So actually, maybe you have to use circulating binaries to represent a decimal fraction precisely. I just want to give you these ideas. Okay, and here is the floating numbers. So did the professor mention this? Yeah. Yes, okay, that's great. So actually how could we transform our floating points to decimal numbers? So we can just use, so the equation should be times 2 exponents minus bias, right, times mantissa, right? That's the equation. So according to this equation, we can just do the multiplications to get our results. So the exponent here is 1110, and it should be 14, right? It should be 14, right? And then 14 minus the bias is 5. The bias is 5 here. So the 14 minus 5 should be 9 here. And so, and the sign here is just 0. So actually, according to the representation here, the final result we get here should be 1 times 2 to 9 times mantissa is just, mantissa actually is this, right? Mantissa is the part after the integer part, and namely the fraction part. So actually we just need to use we can treat it as 0.1111011, right? Actually, this result is just this, and then we just do multiplications to get our final result, right? That's how we transform a floating point to decimal numbers. And that's it. Okay, so the question 5 is that we are going to build a bidirectional circuits to convert between the two sets of codes shown in the table. Define a control signal. If k is equal to 0, we are going to transform BCD code to the XS3 code. If k is equal to 1, we are going to convert XS3 code to BCD code. Actually, what's the relationship between your BCD code and XS3 code? Could anyone tell me? Okay.
Like the XS3 code is the BCD code plus.
Yes, it's just intuitive, right? Just shown in STEM, right? It just say it just XS3 code. Yes, that's quite simple. So actually, if you want to convert BCD code to XS3 code, what do we do? So we just do addition, right? So what we need here is just so if we just transform BCD code to XS3 code, we just need adder. And if we transform but how about XS3 code to BCD code? So actually, normally, intuitively, we are going to need subtractors. But is the subtractor necessary or not? It's not, right? Because actually, so it's quite simple. If we are going to represent the 3 in decimal notations, so actually the subtractions of subtraction BCD code with the 3 can be thought of as the addition as well, right? But their addition number is must be changed. Is it clear? So actually, so if we want to transform the XS3 code to BCD code, what we need to do is to add -3, right? Which namely is just divided 3, or not divided 3, which namely is just subtract 3. Or we can say we just want to add -3, and they're the same. So actually, these two transformations can be both done using one adder. And the only difference is that we are going to use different operand, right? Okay. So what's the problem?
Trick, like in lecture, like if where we sort of like have like I think it was like XOR or something that like causes like the signal we have for 3 to get negated if it's like if the signal is high. Like,
so actually, yes, I think it's quite similar, right? Because it means that when k is 0, we are going to add 0, 0, 1, 1, right? When k is 1, we are going to add the 2's complement of this negate number, and the result should be 1, 1, 0, 1, right?
But in lecture, the example he gave, like it's 1, 1, 0, 0, but then you have like the carry in for like the adder that's like 5 or like k.
The carry in should always be 0, right? Because right?
We can like imitate like a +1 by like changing the carry to 1.
Yeah, yes, actually. So Yeah, yes, maybe yes. Yes, that's correct. Maybe that's another possibility. So you mean that we can just split this 1101 to add 1100 and the carry in should be 1. Okay, that's fine. Yes, that's still a case actually. But here I just what we need to do here is that we just need to we just need to change the operand according to case value, right? And when k is 0, the result should be 0, 0, 1, 1. And when k is 1, the result should be 1, 1. The operand should be 1, 1, 0, 1. So actually, you can find here, no matter what k is, the least significant bit here should always be 1, right? So actually, we can always let the LSB of one operand as 1, and then we will let the bit 1 as not k, right? When k is, because the bit 1 is 1 when k is 0. The bit 1 is 0 when k is 1, right? So actually, for bit 1, we would just use the bit 1 can be represented as not k. And for bit 3 and bit 2, it can be represented as k, right? Right? So that's how we do it. So actually, for the LSB, we will always let it to be 1. And for the remaining 3 bits, we are going to change it according to k. Right? When k is 0, the bit 3 and bit 3 are 0. Bit 3 and bit 2 are 0, and bit 1 is 1. Right? It just corresponds to 0, 0, 1, 1. Right? And when k is 1, the bit 3 and bit 2 are 1, and bit 1 is 0, and bit 0 is 1, actually corresponding to 1, 1, 0, 1, right? It's just corresponding to -3 in 2's complement, right? So after we do the addition, we can get the correct result. We can get our expected result. Is it clear? Is it clear, or is there any problem? We can just come up. You can just propose. We just mention what may be confusing. So actually, I can just, if you just maybe wonder if we can just use addition to get the correct results, let's do one case. Let's say, I think most of you guys are comfortable with k is equal to 0, right? When k is equal to 0, we just do addition with +3, right? And then I think most of you guys are comfortable with this case. But how about k is equal to 1? So if we're going to use the operand as 1101, can we get correct result? So we can just do our example. Let's say, just pick up the excess3. The excess3 code is 0, 1, 0. Right? So what we want is 0, 0, 1, 0. But so we just validate if this addition result is equal to 0, 0, 1, 0, right? So let's do the addition. So 1 + 1 is equal to 0, and we will have a carry out signal, right? And so which means that we will have a carry in signal in bit 1. And 0, 0, 0 plus 1 is equal to 1. And we have not carry out signal. And 1 plus 1 is equal to 0. And we have a carry out signal, right? And we have carry out signal here. 0 plus 1 is equal to 0, right? Right? And we have a carry out signal. But actually, in this case, we find we do not use this carry out signal. So we just use the last 4 bit. And actually, last 4 bit is just corresponding to this. Right? So actually, that's how we do the transformation from the excess-free code to BCD code when k is equal to 1. Okay. And actually, the question 6 is quite similar as question 5. And here is just ask you to use 2 4-bit adders and necessary logic gates to implement a 1-bit decimal adders. Their input and output are all unsigned. So actually, the input output are both BCD. So actually, it's quite similar, right? It's quite similar as question 5. So maybe you can just, I will just give you 1 minute to think of it. How could we, maybe you don't need to just give me the solution. Maybe you can just give me what we need to do when, under what situations. So I will just give you 1 minute. Sorry, I will just.
Wait, why did you leave?
Just give me just a minute to think about it. It's so thoughtful.
But why did you have to leave?
You make it so thoughtful.
So actually, it's quite similar as question 5. We have to consider 2 cases, right? When A plus B is less than 10. So it means that that's fine. We just do addition and we can get correct result, right? And when A plus B is larger than 10, so the summation should be A plus B minus 10. And the carry out signal should be 1. So we have 2 possibilities here, right? So it means that when A plus B is less than 10, or maybe it's less than 10, sorry. So the result should be A plus 10. Summation should be. So, right, if you look at this, so we also used, so for this case, we also have 2 different conditions. When k is equal to 0, k is equal to 1. And in this case, when A plus B is less than 10, we have 1 condition. And when A plus B is larger or equal than 10, we have another possibility. We have another conditions. So actually here, we have to use A plus B, use their comparison result as a control signal, right? Here, we just use K as control signal. So in this case, we're going to use their comparison result. The comparison result is whether A plus B is greater than or equal to 10 as control signal, right? And to control the result we get. So let's say So for example, let's say we get the control signal here. The control signal is S. So we just let's find the relationship with S and S and the summation and CO, right? So actually, if we just get the A plus B is equal to or greater than 10 as signal S, CO, the carry out signal is equal to S, right? Is it clear? Right? And summation result should be A plus B minus 10 times S, right? 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 Is it clear? Is it clear? So actually, but how could we get the control signal S? So that's the case we need to do. So let's say this. The summation of the result A plus B should be what? Should be a 4-bit number or 5-bit number. So first, how many bits we are going to we should use to represent the result A plus B?
It should be, wait, it should be 5.
Yes. Why?
Because we can represent like up to the all the way up to like 9 plus.
Yes. And actually, the 9 plus 9 is equal to 18, right? And because the maximum number we can represent using 4-bit is just 15. So actually, it means that we have to use 5 bits to represent the result A plus B, right? And so actually, let's say we have a 5-bit result. The 5-bit result is let's say this. Sorry, we're very small. And the result, let's say the result is number let's say what? Maybe D. How about D? D4, D3, D2, D1, and D0, right? And so actually that's the summation result of the A plus B, right? And so under which conditions this 5-bit result can be larger than 10 or equal to 10? Just consider these situations. So we just think from the MSB, right? Because so it's quite similar as the computing maximum circuits we talked about last times, right? Right? So if you remember, so we are going to compare the result of A plus B with the number 10. So it's just meaning that we just want to find the maximum numbers between the A plus B and 10. So it's just quite similar as the computing maximum circuits we talked about last times. So how about how to compare the relationship between these 4-bit numbers with these 5-bit numbers with 10? So we just consider from the MSB, right? When the MSB is equal to 1, so the minimal decimal number when the MSB is 1 is 16, right? So when the MSB is equal to 1, then this summation result must be larger than 10, right? Is it clear? So we have these conditions. When D5 is equal to 1, then S is equal to 1, right? Is it clear? And when D5 is 0, D4, sorry, D4 is 0. How could we compare A plus B, the A plus B with 10? So how could we do this? How could we do the comparison? So actually, if we want to these 5-bit numbers is larger than or equal to 10, then the D3 must be 1, right? Is it clear? When D4 is equal to 0, if we want to A plus B is larger than or equal to 10, D3 must be 1, right? Is it clear? D3 must be 1, right? But for D2 and D1, either of it be 1, then we can say A plus B is larger than or equal to 1. But it is larger than or equal to 10, right? When D3 is equal to 1, D2 is equal to 1, then the minimal number we can represent, it represents is 12. So we can say it must larger than this 10. And when D3 is equal to 1, D1 is equal to 1, the minimal number it represents is just 10, right? So we can also say the summation result is larger than or equal to 10. So actually you can see here, so we just end the D3 with D, you can say here, D3 with D1, right? Actually, it means that when D3 and D1 is equal to 1, right? And this AND gate should be D3 is equal to 1 and D2 is equal to 1, right? So we are going to orient these 3 possibilities. So we can say this signal is just S, right? Is that clear? Is it clear? Is it clear? Yeah. So after we get in the S, so the CO is equal to S. And then we can say if S equal to 0 is equal to 0, the result is just this is the summation result of A plus B, right? So the result is equal to A plus B plus 0, right? And when S equal to 1, the result should be A plus B plus minus 10, right? And that's the case. And actually, if we're going to represent it in, so the addition, the operation of this addition should be minus 10. Actually, it will be controlled by the S here. Sorry. And you can just get the final result. Is it clear? So what we do here, the design logic here is that, so we just think of it, what contour, what signal makes our result different, right? So for question 5, it explicitly shows that it is the control signal K. But for the question 6, we have to find what the control signal should be. And then we find that the control signal should be the relationship between the A plus B and 10. So actually we have to, so first construct the control signal. And then we are going to decide the result, the relationship between the result with the control signal, right? And then after getting the relationship between the control signal and the result, we can just finish our design. Is it clear? Okay, that's it. Okay, I think maybe I don't know, maybe we don't have enough times to go through the additional material. So actually the question 7 is just a question we discussed in the review section yesterday. So it just ask you to implement a converter from 3-bit gray code to 3-bit binary code. So actually you just need to know that. So according to the problem set here, so we should use the 3-input binary decoder as the to accept the 3-bit gray code, right? And then after passing these 3-bit binary decoders, we can get a 8-bit output or a one-hot element or no, sorry, the one-hot vector with 8 elements, and only one element could be 1, and all the other elements will be 0, right? So actually, so we will just use the 8-bit output as the input for the 8-input binary encoder, and to get the corresponding binary code. Okay. So actually, I think I already talked about it in last in yesterday review section. So the thing we are going to do here is just swap the order of the elements, right, of the one-hot vector. Is it clear? Because if we want to get the binary code from one-hot elements, we just need to let the corresponding input index to be logic 1, right? For example, if we want to get the binary code 100, we just want to the inputs 4 to be 1, and all the other input are 0, right? But if we just, so for this case, what we want, so for this binary code, we just want as input, right? As the input for the decoder. But for this case, but for the gray code, what we get, we will get a right? Because after passing these 3-bit decoders, that's the one-hot vector we get. So how could we transform this one-hot vector to this one-hot vector? We just swap the order of these elements, right? But actually, in this case, we just care about order of the element 1 instead of the order of other elements, because if we just swap 2 zeros, the vector does not change. So we just need to swap the orders. We just need to swap the order of 1 of the input 1. So actually, in this case, it means that, so let's say, (0 to 7), and this case 1, 2, 3, 4, 1, 2, 3, 4, and it means that in the decimal 4 case, it means that we are going to varying the output 6 with the input 4 together, right? So that we can transform the gray code 110 to the binary code 100. Is it clear? So actually it means that we're going to do the varying. This is the output 6 and this is the input 5. So we'll just connect these two together so that when the gray code is 110, we can get 100. And similarly for the gray code 111, so we're going to connect the output 6 with the input 5, right? So actually, by iterating all these possibilities, we can finish the wiring. Is it clear? Is it clear? Right? So that's the question 7. And here is some review about sequential logic. So actually, the difference between the sequential logic and the combination logic we talk about is that the sequential logic, the output of the sequential logic depends on the states, or actually the state is just the output of the past or the input of the past actually. And you can see here the states captures the relevant information about the past. And you can see here is the feedback, or we can say here is a loop in our sequential logic or a sequential circuit. And here is a typical sequential circuit. And we just call this circuit RF launch. Sorry, here's the word. Launch. So it should be spelled as LATCH, latch. So actually, you can see here. You can see here is the truth table of this latch of this circuit. So actually, you can see here the input is not open. So you can see the expression for this, the Boolean expression for this circuit. So their output, namely their Qn plus 1, is not only depends on S and R, but only depends on the previous output Qn here. So actually for this, to get a truth table for this circuit, so we are going to need 8 entries. But actually we can just simplify the entries. So to 4 entries. We can just simplify the truth table to 4 entries. And for example, when the Qn is equal to 0 and when S is equal to 0, no matter what R is, the Qn plus 1 is always 0. And when there when the R is equal to 1, R is 0, Qn is 0. So the Qn plus 1 is equal to 0. And you can just understand the function of this circuit by just reading the truth tables or reading these, or actually this is the kernel map, right? Actually, or reading from the kernel maps. But you have to understand here. So we just call this launch as RS launch, RS launch. And S here represents set, and R here represents reset. The set here is that when the signal, when the S is 1, so we are going to set the Q as 1. And when the R is 1, it means that we'll, no matter what Q is, we're going to reset Q as 0. And when R and S are both 0, it means that we will maintain the value as previous one, right? When the R is equal to 0, when the S is equal to 0, R is equal to 0, Qn plus 1 is equal to Qn, right? It just maintain the value of Qn. And when the R is 1, it means that we are going to set the value of Qn as 1. When the R is 1, we are going to reset the value of Qn as 0. Is it clear? So actually, because of this definition, we don't care about the case when R, S are both 1, because it has no sense. it doesn't make sense because when we want to reset and set the queue, right? Because it doesn't make any sense. We could not do these two opposite things at the same time. So actually you can see here when R as R are both equal to 1, we don't care about the Qn plus 1 because it doesn't make sense. So for this RS launch, we don't expect the input will be 1, 1. That's it. And actually, the RS launch, the state of the RS launch changed at arbitrary times, right? But depending on the signal of R and S, right? And how fast it's changed depends on when the input changed and how fast the various gates were. So namely, so when the R is changed, the Q will be changed after delay of this XOR gate, right? So actually it also depends on how fast the various gates were, right? So actually because it depends. So what's your problem? Sorry, yeah, sorry, it's a NOR gate. Yes, it's a NOR gate. It's a NOR gate. NOR gate. Right? It's just a NOR gate. Okay, I think maybe we don't have enough time here. I will just show you the tendency form. You can just finish this. The tendency form is quite, I think it's still related to the numerical representations because we don't just have new content told. So actually we still use the numerical representations as their tendency form fractions. And I think this is really simple. And so actually I just have a glance about the quizzes. So I think the quizzes format is quite similar as the problem sets. So manually the problem are manually about the will be manually auto-graded, which means that we will only have unique solutions, but only a few problems will be judged by our TAs and graders. So I think the format is quite similar as quizzes, so don't worry. And the difficulty level is similar as the problem set as well. Okay.
Will stuff from today's discussion be in the quiz tomorrow?
Sorry?
Will everything from today's discussion be in the quiz tomorrow?
No? You mean everything I covered will be quizzes?
Can it be in the quiz? Which parts will be in the quiz and which parts won't be?
You mean which part? So actually, so the quizzes will not have the same questions, but it will relate. So it will have the content about the numerical representations. So the two's complement, one's complement. And then so it will also covering problems about using the existing building blocks to design, to realize a Boolean function.
Is that it? Or are there other stuff?
There do you have some other stuffs? But I couldn't remember, or maybe
Is there like a paper that has those things on it?
paper.
Yeah, like, is there like a list?
I think you will finish through grade scope as well.
But like, is there like a way I can see what's gonna be on it before I start it tomorrow?
You mean you can?
Like, is there like a study guide or something, or like a form with like the things that will be on the test?
I'm sorry, I don't get you.
Is there a document that has the topics that will be in the test tomorrow?
No, actually, I think just we will just cover what you have learned, all the stuff you have learned actually. But
Including
maybe,
yesterday?
sorry,
Does that include yesterday's lecture?
we will not cover. I think maybe you will not cover the sequential logic, but you are going to, you have to. So maybe we will cover until the carry look ahead adders or carry select adders. I think we will cover this, but not about sequential circuits. So all about the combinational logic. So what's your problem?
Can you tell us how many questions?
I think 5 questions actually, and actually maybe for each questions we may have maybe 3 or at most 3 or 4 sub questions.
20 questions.
No, at most maybe just 10, maybe 10s, maybe just. And actually, all these questions, I think this is quite simple. There's no complex questions. There's no maybe there's no really complicated design questions like what we talk about, like the question 6 or question 5. There's no these stuffs, I think. So what's your problem?
So like would the design questions be similar in scale to like maybe the question set that we have on the slide?
Yes. It means that we only have one solutions, one unique solutions. You don't need to worry. So because we just want to auto-grade these design problems, so we will just make it really simple. Don't worry. Oh, what's your problem?
So it's not going to be like the one only question for like POS. And like,
So it's quite similar as the problem set.
oh, okay. So like the problem set's probably would be good into studying.
Yes. Yes, it's quite similar because we just want to auto-grade it. Okay. Okay, that's it. If you have any more questions, you can just ask me. Okay. Great. Just